Morning, everyone. How y'all feeling?
Not a lot of us did. We felt.
People are loud. Maybe they got things going on. For needing help. It's all valid.
So true.
Do you guys have any questions, comments, concerns, etc. before we get started today? All right. Please let me know or interrupt me if there's anything you need.
Wait, I have a question.
Yes.
I saw a TikTok, right? And there was a slinky and a ball, and the slinky like doesn't drop until the top of the slinky touches it, and then it falls. Why? Why doesn't the whole thing fall?
So technically the whole thing is falling.
Yeah, but it stays. Like it defies gravity for like a whole minute before the top hits it, and then it goes down.
So now you're not wrong. But how I would describe it is that the center of mass of the slinky is still descending due to at a constant acceleration because of gravity. And that's kind of how gravity always works. The center of mass of the object is always what is mostly being accelerated. Because the center of mass of something, for a lot of humans, that's somewhere around here. The center of mass is the center of your own gravitational effect, and that means that is the spot that the Earth's gravity is most directly acting on you. And for the slinky, even while fully extended, its center of mass is still somewhere in the center as long as its coils are evenly distributed. So for each frame of the video, the center of the slinky is still descending.
Yeah.
It does look weird, you're right, but the center of mass of the slinky is still descending, and that means the slinky as a whole is still accelerating because of gravity. I would assume that since the center of mass is accelerating, that kind of satisfies the needed gravitational acceleration. So the object as a whole is accelerating, and that makes the universe happy. And therefore, the bottommost coil's not moving yet. The individual bottom coils, their inertia would tell them hold still if you can, because every object's inertia says do whatever you're already doing. So the bottom coils don't want to move until they have to. And they don't necessarily have to move until the falling center of mass catches up and forces them to.
Interesting. It just didn't make sense to me. When I watched it, because I was like, oh, why doesn't it all fall?
Yeah, I mean, you're right. The slinky's kind of weird because it's one object that kind of behaves as a bunch of separate individual objects, because you can think of each coil as a separate moving piece. And you know what, I have a projector. See if I can find the video you're talking about. This might not be the same one, but so, guys already released it. Top of the slinky's there, bottom of the slinky's here. And you're right. Bottom coils don't move until they have to, but the entire time, as the other coils are moving towards it, the center of mass of the slinky is still accelerating down at the correct rate. But each individual lower coil doesn't start moving until it has to, because their own inertia is telling them to stay still until the center of mass catches up at that point. Yes, it looks very weird. It's kind of a glitch. It is kind of a glitch in the matrix, because not only is the whole object falling, but also simultaneously each coil's inertia tells it to stay still.
Yeah, I don't.
So it is kind of a glitch, because it's, the fact that it's multiple coils allows it to both fall and to stay in place at the same time. Most objects that are made of multiple different parts can behave like that, and that kind of includes the human body. A weird amount of the human sensory experience seems to be based on the fact that you are a bunch of different pieces stapled together inside of a skin bag. Namely centripetal force, because your blood can move separately from your nerve endings. So, might come back to that later when we start talking about, multi-part objects and their motion. Did I look at, is that,
Yeah.
it's Monday, I can't talk. Does that feel good for now?
Yeah.
Okay. Any other questions or random thoughts for today?
What are we doing in lab this week?
Lab this week is going to be collisions. Do you guys remember the air tracks that we used about 2 weeks ago now? You're going to be causing collisions on those, rather than have one car rushing towards one side of the track. You're going to have two carts and you're going to slam them into each other. And the main things that you'll be examining are the momentum involved in the collision, also the kinetic energy involved in the collision, because secretly, even though momentum and kinetic energy are different things, they're still related, and because they both are found with M and V, if you have one, you do have the other. So they are connected, and the lab will be partially exploring that connection, so tracking both momentum and kinetic energy through the collisions, but also examining different types of collisions, because sometimes objects stick together, like when on Friday we did the question where the arrow stuck into the log. But there's also plenty of collisions where objects bounce away from each other. That is, the lab will be exploring the differences between elastic collisions, where you get things bouncing away, and separately, inelastic collisions, where the objects tend to stay together as a result. So, one lab that kind of explores a bunch of related concepts and demonstrates the two different types of collisions. Speaking of, we're on normal lab schedule again, so do attend as normal this week. Anything else on your minds? Random or otherwise? I do like the weird ones.
How do frisbees fly?
That's so valid, yeah.
It's funny you ask, because we still don't have a very good answer. Frisbees and also boomerangs, as a related phenomena, are referred to as aerofoils, which is to say that because they are spinning, the air is moving across and under them in weird ways that causes them to fly. Boomerangs just are an added. Boomerangs are basically frisbees, but with the added complication of returning to you. But they're both aerofoils, and kind of like magnets, we still don't have a very good explanation as to why they do what they do. It's obviously related to the motion of the air, but the air is moving very weirdly because the object is spinning and moving forwards at the same time. And there are people who have probably spent their entire careers just studying aerofoils, which is to say, again, frisbees and boomerangs. And I'm not one of those people, so I don't have a very good answer, unfortunately. Sorry. But it's complicated, it's weird, and yet, Aborigines still managed to weaponize it in the case of boomerangs. So they're probably smarter than all of us. Does that address the concern enough for now? I'm sorry I don't have a better answer than weird. Honestly, magnets are still similarly frustrating, I can tell you a lot about magnets, but we still don't really know why magnets. Anything else on your minds? All right. Do please interrupt me if any other questions occur to you on topic or otherwise. What is on topic is on Friday we started chapter 6, which is primarily focused on momentum. Again, a measurement of how difficult something is to stop. Bless you. And we're going to be talking about momentum largely through the lens of collisions, some sort of an interaction between two objects that causes a force between the two, causes the two objects to accelerate, and in the collision, the objects tend to exchange kinetic energy and momentum as they are exerting force and doing work upon each other. Again, on Friday, we looked at a case of an arrow striking a log. The arrow has momentum, and upon the collision, it has to give most of its momentum to the log so that it begins moving. And I ended last time by mentioning there are a few cases where momentum doesn't look like it's conserved, but that it still is. So tapping away real quick to conservation of momentum. Momentum is always conserved in a collision, even if it doesn't look like it is. Technically energy is too, but energy can turn into lots of different forms that makes it hard to track. Momentum has only one form, and that makes it easier to track. But even then, sometimes it still looks like it vanishes, but it doesn't. One of the cases where it looks like it vanishes is noise incoming. When you have a collision between a small object and a really big one, the big object should be gaining momentum in the crash, and yet it doesn't move afterwards, and that's because its mass is too big. It does move, it's just the movement is so tiny and microscopic because of the large mass of the building itself that you just don't notice it. So the momentum is conserved, technically. But there's another scenario where the momentum might not always look like it's conserved, and I want to demonstrate that it still is. And that is in the case of explosions. Explosions, technically speaking, are just weird collisions. Explosions are weird collisions, physically speaking. Main example we're going to do is a cannon, but I'm going to draw another related example real quick to help demonstrate it. Let's see how many class sessions in a row that I can bring up Mythbusters. One of my favorite episodes growing up was the water heater rocket episode, where they took a water heater, they disabled all its safety features, and they cranked the heat up such that the pressure grew and grew and grew until the vessel just voids and explodes. Now, before that happens, how much momentum does this thing have if it's just sitting here slowly boiling? None. It's not moving yet. Even if there's pressure bubbling away inside of it, the physical metal has a velocity of 0, therefore its momentum before kaboom is 0. After kaboom, a bunch of different pieces of metal are all going to fly away in different directions. What is the total momentum now? Total momentum across this entire system. Now, okay, I'm going to rewind slightly. Different question. Does each individual piece of what's left of the water heater have momentum? Yeah, they have mass, they have velocity, they're rocketing away very fast. So each single piece has momentum. But the initial total momentum of the system was 0. And that means, according to this principle, the total final momentum of the system must be 0. How does that happen if each individual piece now somehow has momentum?
Do they cancel out?
They do cancel out because momentum's a vector and each piece is moving in a different direction. Each individual momenta of each single piece still adds up to 0 because the directions cancel out. That's why the pieces literally are flying in every single direction. And that's one of the things we're talking about today. This is one of the cases where momentum might not look like it's conserved because we start with none and then clearly there's momentum now. Where did it come from? But the total is still 0. And that happens because momentum's a vector. The left and right pointing momenta cancel out. The up and down pointing momenta cancel out. So the total is still 0. And I'm going to now backtrack away from this to a more simple example, a cannon. This is a vintage pirate ship type cannon, is my intent here. Big old hunk of cast iron with a chamber inside full of gunpowder and a metal ball. Before you light the fuse, how much momentum is there in this system? 0, nothing's moving yet, like the water heater. After kaboom, cannonball rockets away very fast. So the cannonball has momentum. But what happens to the cannon itself, if you've ever watched a pirate type movie? Pushed back. It goes kathunk and slides backwards, right? That's called recoil. The cannonball is gaining forward momentum from the explosion. The cannon gains backward momentum from the explosion. And what we're going to prove today is that the forward momentum the cannonball gains is equal but opposite to the backward momentum the cannon gains, so that they still add up to 0. So the momentum is still conserved from start to finish. That's our objective today. Questions so far? All right. Before we actually do the math for that, I have a new formula and a new concept to give to you. It's not really a new concept, but it does. This thing has its own unique name for some reason. In the example that we're about to look at, we can tell that the momenta of each object changes from start to finish. Originally, neither separate object has any momentum, and afterwards, they both have momentum. One of them's forwards, one of them's backwards, so they both underwent a change. Someone, centuries ago, decided it would be a great idea to take the term change in momentum and give it its own name. And the name they gave it was impulse. Impulse is just the dedicated term for change in momentum, delta rho. I don't know why they named it, since delta thing seems suitable for most other things in physics. But no, they gave it its own name. And weirder still, they gave it its own variable. And that is also confusingly lowercase j. There is exactly, hold please. Where did it go? Impulse is supposed to be on this thing, I just can't find it. Oh, it even says the word impulse. Okay, this sheet uses capital I. I need to revise this thing so bad. So I'm used to it being lowercase j. Apparently some people still use uppercase I. So That's not confusing. I apologize. Whatever letter it is, impulse is just the dedicated name for change in momentum. And it does have its own, a couple unique formulas. On your formula sheet, right here next to the word impulse, it uses I, and I'm sorry for the inconsistency. I didn't notice what the department sheet used. Impulse equals change in momentum, delta rho, but it also equals force times time. But it also further equals, oh good, I have it over here, mass times change in velocity. There's about 4 different ways you can describe impulse. Its own letter, its designation is change in momentum. If momentum is changing, you commonly find it by just multiplying mass times the change in velocity of the object. But also still, if something is undergoing an impulse, which is just the way of saying its momentum is changing. Undergone an impulse, momentum changed. Those are synonyms. If something has had an impulse happen to it, it happened because a force acted on it for a certain period of time. And that force caused it to accelerate. And if it accelerated, its velocity changed. So every single part of this statement is all connected. Impulse is defined as change in momentum. Momentum changes when velocity changes. Velocity changes when a force causes acceleration over time. And so we are going to use the term impulse to help describe what's happening here. Because not only is the total initial momentum of 0 conserved from start to finish, 2 objects involved in a collision, as long as it's just 2 objects in a single collision, really that's about as complicated as collisions are going to get in this class. The 2 objects should impart the same impulse upon each other. And that's another thing we're about to prove. Right now to start, definition of impulse is change in momentum. The magnitude of impulse is how much the momentum changed. And since it's the change in momentum, it has the same unit as momentum. It's still kilogram meters per second. So, formal vocab word, since we're about to start using it a little more often. Impulse just means change in momentum. I use J because of habit. But apparently your formula sheet says I, so I'm going to have to pick one and be consistent about it. I'm muttering at this point, sorry.
So capital P is power, but the lowercase p or rho is momentum.
Yeah, that's just another reason this formula sheet needs revision. Oh, man. Capital P is supposed to be power, but this old department sheet, which I keep forgetting to advise to get my ADHD medicated, uses capital P for momentum as well. On the notes, I'm trying to use rho, but this thing uses P most of the time. So, I'm going to go ahead and point out every time on here, on this thing, that it uses rho instead of, that it uses P instead of rho, so you can note it for yourself. Momentum, conservation of momentum, and impulse down here all use uppercase P when I would say that should be rho. And that is, I'm saying this to distinguish it from the uppercase P right above impulse and power. Doesn't help that uppercase P is pressure too. Like I said, physics ran out of letters a long time ago. We stole from the Greeks. I don't know why we can't steal from some other alphabets. let's put some numbers to the cannonball. The cannonball has a mass of 15 kilograms. It starts at rest inside of the cannon, and after launch, it is going to fire away at 81 meters per second. This thing is booking it. The cannon itself has a mass of 275 kilograms, because it is just basically a molded lump of cast iron, because those things were heavy. And it is going to get recoiled backwards as a result of the explosion. And we need to figure out how fast, so that we can build the ship around it to accommodate. Also, don't stand behind a cannon that's about to go off. Several pirates probably had a really bad day because they didn't know that. So, we got their masses. We know the initial speed of both objects, which is 0. They're starting at rest. And we know the final speed of the cannonball. We want to eventually end up knowing the final speed of the cannon itself. First question, what is the total momentum in the system before launch? How much momentum is in this image? 0. We know that because both objects have a velocity of 0, so whatever their masses are, they don't have any momentum to start with. And utilizing law of conservation of momentum, what should that make the system's final total momentum? Also still 0. Even though each single object will have its own momenta, momentum's a vector, meaning that forward momentum cancels out with backward momentum, like how forward and backward forces cancel out. So we know it will be 0, but I'm going to be a little bit more specific. I'll write in the momenta for each single object. Momentum final cannon plus momentum final for the cannonball. I'm just going to call it ball so I don't have to write the word cannon over and over again. So just cannon means cannon, ball means cannonball. This is the sum of both objects' final momenta, and we know that it has to add up to 0, because that was the system's initial momentum. And since there's only 2 things here adding up to 0, that implies each object's final momentum should be equal and opposite. However much forward momentum the cannonball gains from the explosion, the cannon will gain the same amount of backwards momentum. It's the only way that they add up to 0. And again, this is meant to demonstrate how the total is still conserved from start to finish, even if there is non-zero momenta on one side. They all still add up to 0. There's a couple different scenarios where this happens. I kind of want to point out at least one of the examples on your homework, just so that you know what it's talking about if you start the homework. There's a homework problem where someone is standing still on ice. They throw something forward and they start sliding backward. Same thing. This is, mathematically speaking, an explosion. So the homework example where someone's sliding on ice, there's also another homework example where someone is floating in space and they do the same thing, throw something forward, they drift backwards. All those types of questions, this same logic applies. Just want to point that out. These are all, mathematically speaking, explosions, even if there's no gunpowder involved. So, next question on our way to the final answer. What is the impulse of the cannonball? That's going to be the cannonball's change in momentum. And there's several different formulas for that. Impulse, change in momentum. The explosion is gonna exert a force on the cannonball for the duration of the explosion, but we don't know that force yet. We do, however, know the mass of the cannonball and its change in velocity. I don't think this one is actually on your formula sheet, so you should write that one in with the other impulse formulas if it isn't. So, since we know the cannonball's final and initial velocities, we can figure out how much momentum it gains from the blast. So impulse, ball, too many L's. Mass of the cannonball times the change in velocity of the cannonball. 15 kilograms times 81 minus 0. And the cannonball's impulse, if my memory is correct, is 1215 kilogram meters per second forwards. That is the change in its momentum from start to finish, which implies that is how much momentum it gains from the explosion. Questions on finding that number? Okay, you're good before moving on? Okay. Now, next and related question, what will the impulse of the cannon be? And I will prove that answer mathematically, but before the math, knowing this, what should the cannon's impulse be in this scenario?
Same number but negative.
Same number but negative. In order for the two final momenta to add up to 0, if the initial momentum was 0, the two final momenta must cancel out, one forward, one backward. And if neither of them had any momenta to begin with, they should both gain the same amount of momentum in the explosion, one pointing forwards, one pointing backwards. And the rule is, two objects in a collision should always have equal and opposite impulses. The reason being, Newton's third law, if one object exerts a force on the second exerts the same but opposite force back. The same but opposite forces are going to act on each object for the same amount of time. So using this other version of the impulse formula, if they're under the same force for the same time, they should share at least the same magnitude of their impulse. They just have to point in opposite directions to keep the universe happy. So, cannon's impulse should be negative 1215, but I am going to mathematically prove how we can jump to that conclusion. I'm going to demonstrate how we can get there. And I'm actually going to start from here. We know that the initial momentum should be 0, but rather than jump straight to that conclusion, I'm going to actually fill in the same information on the left side as I did on the right. I'm going to put in the two initial momenta adding together instead of just skipping straight to 0. Sum of all the initial momenta, that would be the initial momentum of the cannon plus the initial momentum of the cannonball. So, kind of treating this like we did on Friday. We've got the initials adding together on the left versus the finals adding together on the right. Everything here, both sides should add up to 0, but I'm not going to do exactly the same thing as was on Friday. On Friday, we kept all the initials on one side and all the finals on the other, but today I'm going to tweak it slightly. Today, to make it about impulse, I'm going to get both momenta final and initial for the cannon on one side and both momenta, final and initial, for the cannonball on the other. So rather than separating initial from final, we're going to separate cannon from cannonball. To do that, I'm going to bring cannon final to the left and ball initial to the right. So that's going to give us momentum initial cannon minus momentum final cannon equals momentum final cannonball minus momentum initial cannonball. So we just sent one from each side to the other so that both of the cannon's numbers are here and both of the cannonball's numbers are here. Any issues with this? Okay. So what we've done then, what's happened here is that we've changed it from being about the totals on each side to being about the impulse of each object. On the right side, we've now got momentum final cannonball minus momentum initial cannonball. Final anything minus initial of the same thing is the change in that thing. So this is the cannonball's impulse. Final momentum minus initial momentum, the change in momentum of the cannonball. And we've already found what that is, 212. So now instead of this, I'm just gonna fill in the 212, because this is just the impulse of the cannonball, which we've already found. It's the change in momentum of the cannonball. Final minus initial. And the same is technically true of the cannon itself on the right, sorry, on the left. What's weird here though is just that we have initial minus final, whereas delta is always defined as final minus initial. So to get to change in momentum of the cannon itself, I gotta do one quick thing to kind of reverse those signs. I'm gonna distribute out a -1. Distributing out a -1, inverting the signs of these two things, which would take us from momentum initial minus momentum final to negative momentum initial plus momentum final, which is mathematically the same as final minus initial. Negative plus a positive is the same as positive minus a positive. So this, weird as it looks, is impulse of the cannon. Final minus initial. Pulling out this -1, reverse the sign so that it matches the typical final minus initial pattern. So, -1, replacing this with impulse cannon equals 1215. Therefore, the impulse of the cannon must be -1215. The cannonball gains 1215 that way. The cannon must gain 1215 opposite to even everything out. And this is how we can use math to prove it rather than just assume it to be true. So once again, two objects involved in a collision, their impulses should be equal and opposite. So however much momentum one of them gains, the other had to lose, since momentum's conserved, like how energy is. It's one of the things you'll be looking at in the lab this week. So the cannon proper impulse. So -1 times impulse cannon equals 212. Therefore, impulse cannon should be negative. Did I say 212? It's 1215. What's wrong with me? -1215, just implying backwards. Notice equal but opposite, and therefore they do add up to 0, bringing us back to the total being the same from start to finish. How's all that feel before I move on?
Is the impulse always going to be the same as the momentum?
If the objects begin at rest, the impulse will be the same number as the final momentum, because if they start with none, their final would just be what they gain. If they start with a non-zero amount, then it'll be different. For example, actually, we're not going to do this one today, but I have, as another example for another day, using baseball as an example. When the ball approaches the pitcher, it has forward pointing momentum, and after the collision with the bat, it turns around and now has negative pointing momentum. That's a very big impulse, but its initial wasn't zero. So say if it had 40 forwards and wound up with 30 backwards, that would be an impulse of negative 70. Does that track? Okay. So it depends on if the object had any momentum to begin with. Does that answer the question? Okay. Now back to the cannon itself. Now that we know the impulse of both objects, we can figure out both the force of the blast and the recoil speed of the cannon. This part, the force of the blast, if the launch took 0.05 seconds, how much force was involved? The way that these cannons work is you physically load a bunch of gunpowder in there. The point of the fuse on the back was you light the fuse, it takes the fire to the gunpowder, then the gunpowder physically explodes, blasting the cannonball out of the only opening of the cannon. So the force here is going to be the force of that physical explosion. And that force is going to act forwards on the cannonball and backwards on the cannon. And we'd like to know how much force that is, because you need to make sure that the cannon itself can handle that much force. You don't want it shattering. You don't even want the back piece just opening because of that much force, because that'll really ruin your day if you were standing behind the thing. We're running out of room over here, so we'll take these next parts over here. So you need to know how much force the blast will cause to make sure that the lump of cast iron you're using can handle it. So I'm going to rewrite all the many versions of saying impulse real quick. Impulse is change in momentum. Momentum changes when a mass's velocity changes. Specifically, this happens when force acts on something for an amount of time. We know that force causes acceleration, and if you accelerate for a certain amount of time, your velocity changes. Secretly, this all connects directly back to Newton's second law. It's not secret, actually. That's surprisingly related fact. I know we've been talking about Newton's second law as F equals ma, but that's not actually the form that Newton written in. Newton wrote the law like this. And after the fact, people started writing it as F equals ma because that translates to the same thing. But technically, this is just a variation of Newton's second law. If I take the time and send it over here, m delta v over t equals f. Delta v over t is acceleration. So it's still Newton's second law, just a different application. Surprisingly, Newton did more work with momentum, or might have done more work with momentum than he did with normal proper force. Which again kind of makes it weird that we didn't put either of his names on the momentum unit. Anyway, back to explosions. Since we know the impulse of the cannonball and of the cannon, we can figure out how much force the explosion caused if we know the time the explosion lasted. Because all forces only are acting for a certain amount of time, while collisions only happen over a certain amount of time. Usually you'll blink and you'll miss it, but it is a certain number of seconds. In this case, the whole blast happened in 0.05 seconds. So impulse equals F times t. Both objects have a magnitude of impulse of 1215, and the unknown force took place over 0.05 seconds. So 1215 over 0.05 should give, please correct me if I'm wrong, over 24,000 newtons. That's a lot of gunpowder. That is a big boom. It takes a pretty big explosion to launch a cast iron cannonball at, 81 meters per second. But they're only getting a few shots in, and again, you need a very sturdy cannon to be able to not blow up when this happens inside of it. That's the force involved. All collisions, all explosions have some force that is causing all of this. So that is the source of the F term in the impulse formula. It's the force that causes the change in velocity of the objects. It's the force that is doing the work to transfer momentum and energy. So, very last question, finally after all that. What will the recoil speed of the cannon actually be? We know the impulse of the cannon, we know the mass of the cannon, therefore we can figure out the change in velocity of the cannon. So negative 1215 equals 275 kilograms times VF minus V initial. We know the initial speed is 0 because the cannon was stationary before the blast. Please correct me if your math differs, but I've got negative 4.4 meters per second, which isn't slow. I want to point out that means in 1 second, the cannon could be 4.5 meters behind where it was in 1 second. Which again, if you're standing within 4.5 meters of the tail end of the cannon, means you might not have shins anymore. And it's why on old, well, not even pirate ships, any ship with a cannon, pirate or otherwise, they usually had the cannons along rails so that it had space to blast backwards, but that the rails would stop it from just rolling all the way to the other side of the boat. And modern artillery of this nature is usually just bolted down. So, how do all of the aforementioned concepts feel right now? All right. That'll be it for today. Do bring these notes to lab whenever you have lab. Lab will utilize these concepts, and it will also explore how different types of collisions affect what ends up happening in them. The two different types are inelastic, if things don't bounce off of each other, which is like the arrow embedding itself in a log, or like modern car crashes where everything just kind of crumples together. This is different to elastic collisions where things bounce off of each other, like when I throw a golf ball at the wall. Lab will explore all of this stuff in addition to looking at those two different types, determining the differences between them. Let me know if you guys need anything, and have a wonderful day. Yeah, the trash can vanished, sorry.